Okay, so I will dive into the internals of the compiler quite a bit. I'm not sure if that will be helpful for everyone or be understandable that much, but I'm trying to give an impression of what we are doing in the final step after what Harry was talking about for generating actual EVM bytecode from Yul. So you probably in the last talks have already heard that Yul is a thin, low-level abstraction over EVM opcodes, but it retains more structure than actually a list of opcodes. So you have control flow structures, user-defined functions, variables, and all that stuff. And you don't need to deal with the nitty details and the explicit jumps or explicit stack manipulations, because that's abstracted away in Yul. So there is still something going on in the translation from Yul to EVM bytecode. But there is actually a very trivial transformation from Yul to EVM bytecode. So I hope you are familiar with this format. That's EVM assembly. So if I have a constant here, that's actually a push. But yeah, let's look through the example here. I hope it's readable. So the trivial transformation from Yul to EVM assembly just walks down the lines of the Yul AST basically, and for an expression, for the call data load, for example, here evaluates the arguments right to left. Here it's only one argument, that's the 0, so I first have the 0, then immediately can emit the call data load, and then I call this value I just generated x, so I have to remember that this is the position of the variable x on stack. Then the next part that happens, I have an if, so I need to evaluate the condition of this if. The if condition is a function, so again, right to left, I have the 15. Then the x, I remember I stored it in the now second deepest slot on the stack, so I dub it up again, and then execute the built-in functions. So yeah, a function call is just right to left, and the function. Then to actually really move line to line, I want to first handle the if body, so I negate the condition to jump over it if it's false. And for the reverter I have in here, same thing again, I trivially evaluate right to left, so I push 2 zeros and revert. And even if that wasn't a revert, if this was an M store, for example, I could just fall through and end in the joint control flow in the end of this block, which is where the variable x falls out of scope, so it's popped. So this is the very trivial, simple transformation from Yul to EVM. But the first question one can ask is this the best one can do? So this is actually what happens if you just invoke the compiler to generate EVM assembly from Yul without telling it to optimize things. So the left-hand side is just for what I showed you. But you will realize you have this dub here, you will have the ES0 here, and a pop in the end, which are all basically redundant. Yeah. So I can get rid of all of them. And the optimized transformation looks quite different. You have all this stuff saved. And in the rest of the talk, I will explain how we get there. Okay, so the goals with doing a more complex transformation than the trivial one is, of course, to avoid unnecessary swaps, dubs, and stuff like that. And what I failed to mention is that I also here have the negation removed, so I don't jump across the block anymore. The ES0 is eliminated by reordering the basic control flow blocks. So that's also something that's a less trivial transformation than the naive approach. And that's one thing. The more important thing is to avoid stack to deep errors. We will get to how that works. And of course, it's nice that there is a trivial and naive trivial simple approach, because that's very robust. And we want to not lose anything in that regard. So we want to keeping things safe. So the approach for code generation should remain simple and robust. Let me quote simple and underline robust, because the transformation in the end is rather complex, but it's designed in such a way that it's as robust as a simpler one would be. So yeah, the basic approach is to split this process into 3 steps. The first one is we generate a control flow graph from the Yul-AST. That's a very simple transformation. That's basically the same as the naive code generation would do, just we don't generate EVM bytecode, but we store the stuff in a data structure. The second step is then to annotate this control flow graph with explicit full stack layouts at the beginning and the end of each block and between each operation. We determine a full stack layout that would tell you which stack slot would contain which value, which variable, and so on. And this transformation is complex because we need to avoid stack issues, stack to deep errors, for example. We need to have freedom in generating these layouts to use the space efficiently. Then, based on that, we have again a simple step that then just actually generates the opcodes from the annotated stack layouts from the control flow graph. So I walk the control flow graph and use the stack layouts to generate code. But the nice thing is that I can validate the correctness against the control flow graph I generated in the first step. So I can, basically, the idea is I could replace the step 2 with randomly generated stack layouts, and only those that are actually would lead to valid bytecode would pass the third step. So while the middle step can be complicated, we don't lose any safety in the process. So yeah, I already mentioned this basically. So the control flow graph generation is similar to the direct opcode generation. It splits the Yul code into basic control flow blocks and those basic blocks into sequences of operations with inputs and outputs. I have an example from the same snippet we started from. So this is the same Yul snippet as before. This is the control flow graph we generate. So we enter this block of Yul. Then the first operation is the call data load that takes 0 as an input, generates a temporary output. Then I call this temporary output x. That's an assignment. Assignments of variable declarations don't need to be distinguished in this representation. Then the last thing in this first basic block is the comparison. That still, again, has 2 inputs, 1 temporary as output. That's the first basic block. And then I have a conditional, the if is the conditional, that depends on the output of this last operation. In the 0 case, I just get to the after the if control flow, which is empty in this case. In the non-zero case, I use the word pass. Actually, there's already a slight optimization in here. If this wouldn't revert, I would not just have an arrow to terminating state here, but I would have a connection to this block after the if. Because if it was an M-store and not a word, I would continue after the if. But yeah, I hope you can see that the transformation from the Yul code to this control flow representation is easy and trivial. So this is easy to get right. The second step I was mentioning before is then to algorithmically generate full stack layouts. By full stack layouts, I mean relative to the current function, because in a call chain, I cannot know what happened before I entered the current function. But it's the full stack representations relative to the base of the current Yul function. And for each basic block, in the beginning, I have an entry layout. Then for each operation, I have a layout before and after this operation, and then an exit layout of the block. This is done bottom up and backwards. I will explain that in an example in a minute. And this will automatically yield to more optimal layouts than the naive top-down approach. And we'll try to maintain optimal locations for variables and stack at all times. We need on control flow joins to consolidate stack layouts, because if I jump to different locations, depending on some condition, I need to have the same stack at all sites. And one of the major important parts is I want to avoid the necessity to access stack slots that are deep in the stack. which are no longer reachable because the EVM only gives me access to 16 slots. So yeah, I start from the control flow graph I had before, and this is what the stack layout looks like. So I walk this graph from its ends, from the main exit and the terminate exit. In the main exit, the last block does nothing, so it ends and starts with an empty stack layout. The terminating block also ends with an empty one. The revert needs 2 inputs. So before the revert, I need these 2 things on stack. But those are constants. I can generate them on the fly. So they don't need to already be there when I enter this block. So yeah, this block entry has an empty layout. So in this case, consolidating the control flow between these 2 blocks is trivial because both are empty. If there was some stuff that these blocks required, I would need to find the optimal layout to have before jumping to this block that would make it as cheap as possible in both of these blocks later to achieve this layout by swapping and dumping. That's a non-trivial thing. I will not talk about how that works in practice. The good thing is it can go wrong regardless what we do. We could generate it at random, and it would still only pass if it actually is a valid layout. Okay, and the first block here, I think I have in larger print. So still, we walk backwards. So this greater than operation represents the result I use as a condition for jumping. So the exit of the block needs this temporary. That's the output of the last operation. That needs 2 inputs, the 15 and the x, that I want as the output of the last operation, which is the assignment of x, which tells me what value I want here to have in this x, and yeah, so forth. Note, however, that here, this 15 is a constant. I could generate that on the fly, but if I did, I would need to swap it. If I don't, I need to generate it in the beginning. See that? Yeah. I'll have EVM assembly generated from that later. Maybe that will make that visible. Okay, and the third step is then to use this control flow graph and the annotations for the stack layouts to actually generate EVM bytecode. For that, we maintain a local symbolic copy of the stack during the process and validate and perform all the operations that the outputted assembly does and validate that the stack layouts conform to the requirements that were described by the control flow graph earlier. That's the main safety mechanism there. And yeah. So here we see the generation emphasized. So this is the stack layouts I described earlier. So I begin, that's again a top-down generation now, that's very trivial. I begin from an empty stack, then the layout tells me I want 15.0 on the stack. So I have a black box operation that generates an arbitrary stack layout from another stack layout. I'll get to that if I have the time. And yeah, I generate this stack by pushing these values, then perform the operation, and yeah, walk this path down, emitting opcodes. I think I need to hurry up. But yeah, I can validate at each of these steps. That's the control flow graph I had at the beginning. So before performing this call data load operation, the control flow graph that was easy to generate tells me I need a 0 as input. I can validate during the actual code generation that I have a 0 on my symbolic stack, so that's fine. The control flow graph also tells me that this outputs something, so I can, in my symbolic stack representation, replace this 0 by this symbolic output and continue. And at each step, validate that actually what I had as a specification for what my code should do in the control flow graph is actually what the code will do. Now, a problem with that, which I will have to skim through, is that minor changes can have non-local effects. So, just if we have a really tiny, actually semantically equivalent change in the Yul code, the control flow graph will remain the same. Then the stack layouts in this area here, I will require the 15 at the top of the stack, so I can generate that on the fly without cost, so I don't drag it along. So the very trivial change in this part affects in the bytecode, in the emitted bytecode in the end, that this 15 moves from the very top down here. Yeah, stack shuffling I skip. So yeah, that will be a problem. I'll get to that in the end for debuggers and tooling. Because, yeah, the stack shuffling and the stack generation will also, yeah, add copies of variables if I would otherwise not reach them again in the end due to stack to deep errors, stuff like that. So what this entire mechanism brings me is the freedom to do complex transformations on these stack layouts that will allow us to generate code even if I have a lot of variables. But that means that tooling will have a hard time to reproduce that. So we need to get to debug data that will actually tell tooling what we did instead of trying to reproduce what we do there. But we have this information, so we just need to come up with a format to outputting it. So yeah, this has come up before today and in a lot of other talks and also on Monday in formal verification context. We need debugging formats for this stuff. And yeah, there have been efforts to define debugging format for that, but I mean, we don't want to guess which format for this stuff actually suits tooling and debuggers best. So we want to have a discussion with tooling about this. So yeah. Yeah, I think I shouldn't have heard that much. Yeah, let me argue the point why this transformation is a good thing. So it actually is, we had those two goals in the beginning, that it's more efficient and that I get rid of the stack to deep errors, and both seem to work out. So I have a reduction in gas costs by a few percentage points and even more so a reduction in code size. So that's nice. And the more relevant thing even maybe is that I get rid of almost all stack to deep errors with this mechanism, because the stack layout generation can more aggressively save stack slots if otherwise I could not reach stack slots anymore, or if that fails, it can give feedback to the compiler in the sense that exactly one of those stack slots or variables, if I can eliminate them, then I would still be able to generate code, and I can then move exactly those variables to memory, which, yeah, is something that then the Yul optimizer would do, and then we could run the actual generation again. So yeah, I hope that wasn't too much and too confusing, but yeah, I think I'm out of time, and yeah, so thank you. Questions?
Okay, I just want to make sure I understood something that you said. If we use this via IR optimizer, then we're less likely to get stack to deep errors? Is that what?
It's almost impossible. So, I mean, I'm saying almost. I mean, okay. there's a few caveats. I mean, if you use inline assembly, we recently introduced the mechanism of inline assembly being annotated as memory safe. Okay. Because that's a prerequisite for being able to move variables to memory. Yeah, the documentation explains the details on that process. That's one caveat. The other one is if you have recursive functions. Okay. Inside recursive function, because we assign static locations in memory for variables, we can't do that in recursive function calls because it would override the variables in the recursions. So in recursive functions, you may also still run into stack deep errors. And there may be occasions in which the mechanisms fail. But please report them, because in optimized via code generation, we consider that a proper bug that I will look into and try to solve. Okay.
Well, I'm very excited about that anyways.
Yeah, I hope it works.
Yeah, So you talked about the fact that you can do some changes that have like non-local effects, right? And you showed the greater than, less than example. I imagine that also makes it hard to know when to make those changes. I'm curious, like, if there are any like heuristics, or how do you do that? And in particular, also, there's this issue about using something, I think it's called the tree graph algorithm for the stack scheduling. I was curious if you kept looking into that or have any plans.
Yeah, we looked into that. I don't quite remember it exactly right now. I think, wasn't that a translation? I mean, if we're talking about the same thing, a translation algorithm from register machines to stack machines.
Yes.
Yeah, that doesn't really apply to the situation. I mean, we tried to use the mechanisms, but yeah, it doesn't fit well. As for the strategies, for example, in this example where I have the 15 early, that's what naturally happens if I choose the bottom-up approach, and that naturally produces rather optimal code. But then I have this 15 on the stack the whole time. So this is not just a simple call data load, but accesses something that was deeper in the stack that has to access past this 15. So what we do, we try to do the optimal thing. If that tries to access something that's too deep in the stack, we switch strategies. And then we would push constants as late as possible compared to at the optimal time, which will result in some swapping, but will save one stack slot that will allow to generate the code ideally. More questions?
Is there a reason that, I guess, putting stack variables into memory is seen as a last resort, or is there kind of like an earlier break line that can be looked at? Do you have a reason?
I mean, it costs more.
Okay.
That's one thing. The other thing is you need the stuff on the stack eventually to perform the operations on. Then also, for recursive functions, you would need actual memory management, because then you have dynamics, frames in memory that you can't just accumulate because they could grow infinitely. And yeah,
Makes sense.
Maybe that's enough.
Yep, thanks for the talk.